We'll proceed in parameterization of surface in calculus. Parameterization of a surface in calculus. Parameterization of a line, parameterization of a curve is one-dimensional parameterization. Means the net calculation happens in xy plane and independent component is only one, that is x. Whereas parameterization for the surface where independent component is xy plane, there is always one independent component. Either it is x-axis or xy plane. If it is xy plane independent component, if independent component is xy plane, then x and y both are independent. So the aim is we will see kind of parameterization for independent component being x and y both. Okay, so both being independent, where dependent is z-axis fxy. In 2D, the dependent is fx, independent is x-axis. So we have seen it. So if I have a if I have a function fx, okay, so consider that this is x-axis and I have a function fx over x-axis. And then if I do the integration of fx along x-axis, then it is fx dx. Integrand is fx and then integration with dx, fx dx. Sometimes fx is very difficult, like the square root of a square minus x square, 1 by square root of a square minus x square dx. If that is the fx, then calculating this integration becomes impossible. In that sense, what the x is independent component here, x, we make it dependent and we take another independent component as u. So x is dependent upon u and y is dependent upon x. Now we modify this as like I can take x equal to a cos u. A cos u. Now I have u and function over u plane and x and function over x, 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 x and function over x plane and u and function over u plane. And now this x and u, the mapping is through a function called g. So if I have dependent component y and it is dependent upon variable x, then there is a function relationship, that is fx equal to function over x equal to y. Similarly, if I have independent component as u and x being dependent on it, then there is a function that relates u and x is gu. Function over u is gu. Gu relates the u to x. Gu relates u to x. Okay, so that is the relationship. I believe it's all right. Now the question arises is that how it makes our life easy. Okay, if that is the case, then I have to change this full integration into the plane of u and function over u. So if I say x equal to u cos u, then it becomes 1 by a square root of 1 minus cos square u. Then it becomes u sin u, 1 by a sin u. Initially it was 1 by square root of a square minus x square, that is function over x fx dx. Now square root of a square minus x square becomes a square minus a square cos square u. Now a come out and then 1 minus square root of cos square u becomes sin u. What about dx? Dx is same as dx by du into du. So dx by du is called Jacobian and dx by du is a minus sin u du. Dx by du I mean dx by du. So dx by du is minus a minus sine u. So now net is 1 by a sine u, and then the numerator is minus a sine u du. Okay, my idea is not to do integration, but this is how it is. Now someone can proceed on it, and it is minus du. Integration is minus u. Now minus u, when x equal to a cos u, u equal to cos inverse x of a. Someone can bring it back into xy plane. So it is minus cos inverse x by a, net integration. How it is easy. Now tell me, if this is the integration, how someone can bring with 1 minus square root of a square minus x square. The integration is minus cos inverse x by a, not possible. Now changing it to polar coordinate system, it become easy. Now same limit, whatever the limit was, someone can specify and get the result. This is the charisma. This is the charm of parameterization. What is parameterization? So if I have independent component as x and x equal to g over u, this is called parameterization. G is a new function for which parameter is u. This is parameterization. Parameterization is nothing but integration by substitution. Integration by substitution. Integration by substitution, in the sense x is substituted to a cos u, whereas parameterization is similar thing, but it is more clear now, because parameterization talks about introducing different plane at all. Like we are introducing a new plane called u. We are introducing new plane as u plane. Earlier we had one plane called x plane, x fx. Now u function over u explain, u explain. Okay, so this is the scenario. Now this is parameterization. Whatever the independent variable we have, we now substitute with the function with a parameter of some other independent variable, making our the independent variable as dependent. Okay, now consider I have fxy. Consider I have a xy plane, and there is a surface on top of it called fxy. If I integrate fxy along xy plane, it gives me the volume. So volume calculation in 3D plane. Now we are coming to parameterization of surface. Till now we saw parameterization of a curve. Now if I have a xy plane and there is a surface, if I integrate this fxy along xy plane, I get the volume underneath fxy dxy plane, and then integration over for the full surface. Like a sphere, I want to calculate the volume of a sphere. Volume of a sphere, the fxy equal to square root of a square minus x square minus y square, because equation of a sphere is x square plus y square plus z square equal to a square. If that is the case, then z equal to square root of a square minus x square minus y square. fxy equal to square root of a square minus x square minus y square. If that is the case, then what is the volume? fxy dxy plane. dxy plane is in Cartesian coordinate. I can say dx dy. Now it is square root of a square minus x square minus y square. Both are independent variables, x and y both. Y is not dependent upon x. Only fxy is dependent. Function over x comma y is dependent upon x and y both. In fact, fxy is dependent upon xy plane. If that is the case, then the square root of a square minus x square minus y square dx dy, no one can calculate. There, the parameterization of surface comes into the picture. So since we are integrating over xy plane, we can go for polar coordinate again. Let x equal to a cos u, and y equal to a sin u, that is the polar coordinate system. Then it is square root of a square minus x square minus y square. A I can keep outside, and square root of, I mean I mean, I'm I'm sorry. I said x equal to a cos u, x equal to r cos u, not two independent variables there also. U and r. Let's say theta. I believe it is better. So x equal to r cos theta and y equal to r sin theta. Now our xy plane that has independent variable as x and y, xy plane independent variable as x and y, and now we are landing up into another plane, that is r theta plane. Okay, so we have now xy plane and r theta plane. Now xy plane, if I see xy plane and r theta plane, then there what is the relationship between xy plane and r theta plane? What is the relationship between z in xy plane? If it is xy plane and height is z, that is fxy, that is fxy. The relationship is function over x and y is z. What is the relationship between r theta plane and xy plane? There is a function which associates this. That function is g. So x equal to g, g is a function over r and theta. Y equal to h is a function over r and theta. Y equal to h r theta. X equal to g r theta. X equal to r cos theta. Y equal to r sin theta. Clearly both are different function over r and theta. My life is easy. So now I can substitute square root of a square root of a square minus x square minus y square. Square root of a square minus x square minus y square. That would resolve into a square minus r square, square root. What were dx dy? Gone. What about dx dy? That is nothing but dxy plane. D of xy plane. D of xy plane is same as d of xy plane by d of r theta plane into d of r theta plane. D of xy plane divided by d of r theta plane multiplied by d of r theta plane. Same thing, right? So d of r theta, anyway it is completely into r theta now. That is a square root of a square minus r square. Cos square sin square theta gone. So that is the now. But dx dy is nothing but d of xy plane by d of r theta plane into d of r theta plane. This is Jacobian. D of xy plane by d of r theta plane is Jacobian. How I can find this amount? But I know if it is xy plane, equivalent of xy plane, any dA area on xy plane is dA, then in r theta plane that is r d theta dr. So silently I can replace with dx dy with r d theta dr. Very nice. Now I can do a square root of a square minus r square and then r d theta dr. So r square root of a square minus r square, the integration is I believe minus 1 by 3 a square minus r square to the power 3 by 2. Because if I do differentiation back, then it will come as same r square root of a square minus r square. Minus 1 by 3 and then in braces a square minus r square to the power 3 by 2. If that is the case, minus 1 by 3 and bracket a square minus r square to the power 3 by 2, if that is the case, then minus 1 by 3 braces a square minus r square to the power 3 by 2. That is the integration for the dr. Now r is from 0 to a, that is the radius of the sphere. A if I substitute, then gone. 0 if I substitute, then it becomes a to the power 3 minus gone. So a to the power 3 by 3 and then theta for 2 pi So now it is 2 pi a to the power 3 by 3. This is the volume of hemisphere. So net, whatever it is, this is the integration. We are not going into calculating the hemisphere volume. This is the integration. So if this is the integration above the xy plane for a sphere which is centered at the origin, then it is 2 pi a to the power 2 pi a to the power, okay, so I believe, okay, so a square 2 pi a to the power 3 by 3. Okay, that is the net kind of. So radius I just said 0 to a, and then it is theta is 0 to 2 pi. But whatever the integration we are getting, so first we got integration as a square minus 1 by 3 minus 1 by 3 a square minus r square to the power 3 by 2, and theta integration is theta, d theta integration is d theta. Can someone bring it back into Cartesian coordinate system where x equal to r cos theta and y equal to r sin theta? Very difficult. Someone can get, I am not saying someone cannot get. Then y by x equal to tan theta. Theta equal to tan inverse of y by x. So theta, what we are getting, seeing here, it is tan inverse of y by x, a square minus r square. So r, similar way I can get the r also. So we will do, someone can do some calculation. X square plus y square equal to r square. Then r equal to square root r square. So it is a square minus, and in bracket x square plus y square full whole to the power 3 by 2 into tan inverse y by x. This is the integration. Can someone believe it? And now x is minus a to a, y is minus a to a. Let's try. So x is minus a to a, y is minus a to a. Okay, so a square, if I put upper a square and y also a square, first let resolve x, then it is a square minus x square minus y square. So a square minus x square, so that is gone. Now minus y square remains here. Okay, minus y square to the power 3 by 2 minus y to the power 3. Okay, so that remains minus, and then minus a I have to place. Minus a if I place and x square, result would be same, something like 2y to the power 3, something like that. And then tan inverse y by x, x will be a. Now I have to set y minus a to a, and then you try to solve it, and it should come tan inverse, I believe tan inverse 1 will come. So tan inverse 1 will be pi by 4. So pi by 4 and pi 4. So it should come as 2 pi a to the power 3. It is, I believe, exciting, thrilling to calculate something in r theta plane and get it back in Cartesian coordinate system and apply the same the limit, that is minus a to a and y minus a to a. Or if someone receives it at 2 pi a to the power 3, if someone receives it as minus 1 by 3 a square minus r square to the power 3 by 2 as the first integration, calculate what is r 0 to a. We are saying r is 0 to a. X square plus y square equal to r square. X square plus y square equal to r square. Now x is minus a, x is minus a to a, and y is also minus a to a. Okay, so what would be its limit? So someone has to calculate that. So this is, I believe it is not that straightforward. So minus x square plus y square equal to r square. So x is minus a and y is minus a. Then it becomes 2a square. And when both are a, it is 2a square. But that is not true. r should be 0 to a. R should be 0 to a. So someone has to use the intelligence. So we will do that. So two ways to calculate the integration. First is change it into another coordinate system, that is parameterization. Calculate the integration, and then on top of integration get it back into the Cartesian coordinate again and apply the limit, or change the limit into the other coordinate system r theta plane and get the integration, whatever it is. Now the question arises is, what is guarantee that I find solution in polar coordinate system? I find solution in whatever the problem I have. Right now it was square root of a square minus x square minus y square dx dy, and we use polar coordinate system, and dx dy become r d theta dr. What is guarantee that every fxy, the way like consider fxy equal to 1 by x square minus y square, x square minus y square, 1 by x square, x minus y to the power 3, 1 by, and denominator is in bracket x minus y to the power 3, and then dx dy. Okay, you may not use polar, you may not use cylindrical, you may not use spherical. You may use something different. If you use something different, r, theta, uv, whatever, so if you take anything uv, then the function of parameterization, the mapping, would not be polar one. That is r cos theta and r sin theta we took. In that fashion, we don't know what is dx and dy. If I change this x and y 1 by, and in bracket x minus y to the power 3 is the integrand, then, and dx dy. So if I take a, like, consider u equal to x minus y and v equal to x plus y. This is what I am thinking, that it is 1 by u to the power 3. Simple, but not simple is dx dy. Dx dy, how I can convert into du dv? If it was polar, then it was r d theta dr. Here we are landing into actual heat of parameterization. What is the actual heat of parameterization is this. Okay, let's calculate the the surface area of any volume. Then we go by parametric way. Parametric vector. Parametric vector is, if I have a xy plane and there is a surface, then I take any point on the surface, and from origin I draw a position vector that comes as xi plus yj plus zk. Now this is the vector. Now to solve the issue, we do parameterization and we introduce another plane called UV plane. Another plane called UV plane. If that is the case, where the z xi plus yj plus zk is a point on the sphere, then z is function over x and y only. So it is xi plus yj plus fxyk. Now to solve it, I have another plane called UV plane. Now x equal to g uv, y equal to h uv. If that is the case, then I call it as parametric vector, r vector in bracket u comma v. This is a new vector that is a kind of function over u and v, equal to g uvi plus h uvj plus f x comma y. So f h uv comma g uv comma h uv k. If that is the case, then how we proceeded to find the curve length in 2D. In 3D, we are proceeding to find the surface length, surface area. To get the curve length, the independent variable was only one, that was xi plus fxj. Now if I did parameterization, it becomes r vector of u equal to gui plus f guj. then dr by du, dr by du, that is nothing but dgu by dui plus d plus dfgu by duj. Okay, if this is the vector, that is the gradient vector of the position vector, calculate the magnitude of it and integrate it along du. You get the curve length. Similarly, we will do it. We are trying to calculate surface area of a 3D. If this is xy plane and this is a 3D, in 3D surface, there is surface. If I take any point of the surface, that surface in Cartesian coordinate then can be represented as xi plus yj plus zk. If that is the case, that is the point on the surface. If I draw from origin, if I draw a position vector, then it is xi plus yj plus zk, where z is the height, that is function over x comma y. That is function over x comma y means fxy. So this position vector p is xi plus yj plus fxy k. We are trying to calculate surface area of the sphere. We calculated length of a curve as a position vector xi plus yj. Now if I do parameterization, then x equal to gui plus fguj. That is the parametric vector ru. dr by du will give the gradient of this vector. dgu by dui plus dfgu double bracket close by duj. Calculate the magnitude of this vector. Calculate the magnitude of this vector. If you calculate magnitude of this gradient vector and integrate along, magnitude of this vector will come as dgu by du whole square plus f dfgu close double close by du whole square root and integration along du. If I wanted to do in Cartesian coordinate itself, it was xi plus yj. Differentiating with x was I plus dy by dxj. Now its magnitude is 1 square plus dy by dx whole square root dx. That was the curve length. Velocity vector, integrate it, you will get the curve length. Similarly, if I transform into another variable, and if I transform into another variable, that is u, then it is dx by du. This is now I can call dx by du plus dy by du. And then if I take the magnitude dx by du whole square plus dy by du whole square root du. Okay, whatever it is. Or what we had 1 square plus dy by dx whole square root dx. Now at runtime, can I do parameterization? I did all computation through Cartesian, and at runtime can I do, because what I am seeing 1 by 1 plus dy by dx whole square root, whatever expression I am getting, that is very difficult to integrate. In that case, at the runtime, at the end, can I change it to parametric vector? Can I change it? Can I do parameterization? Yes, you can do. But dx will be dx by du into du. Dx by du you have to calculate. At the end, dx by du you have to calculate. So let's calculate the surface area with the Cartesian coordinate system at all. So if I have a position vector at surface P, then the point P, then position vector is xi plus yj plus zk. Then what is the surface area? Now there are two independent components, x and y. Xi plus yj plus zk. Z is function over x and y only. Fxyk. Two independent. I cannot do one differentiation. I can differentiate with x-axis, then it will become dp by dx. What is differentiation along the x-axis? Consider this is the xy plane. I am just keeping it, and this is the surface. If this is the surface and if this is the point P, if I calculate dp by dx, I am trying to calculate the gradient in xz plane. If I do dp by dy, then I am trying to calculate the gradient in yz plane. At any moment P, if I do dp by dx, consider it is here where the normal is like this. because gradient will be tangent. Then dp by dx is like this. dp by dy is like this. So at that point, dp by dx, at that point, dp by dx would be like this and dp by dy would be like this, slanted. Okay, can you see it? If you are lucky, like if I am taking like this surface and if I go on top, then dp by dx will be flat, dp by dy will be flat. In that case, it is like this. But other places it can be like this, some places it can be like this, like this, like this. Okay, if I have dp by dx, if I have dp by dy, if I do cross product, because both are vectors, if I calculate cross product, I get the area velocity vector. dp by dx cross dp by dy will give me the area velocity vector, because it's a single one differentiation is done. Now this velocity vector, if I integrate along xy plane, it will give me the surface area. So dp by dx cross dp by dy, it gives the area velocity area vector. If I integrate with xy plane, I get the displacement area. This is what we want. So you calculate the dp by dx cross dp by dy, that is the area velocity vector, calculate the magnitude and integrate it along xy plane. You remember, the integration of velocity is displacement. Integration of acceleration is velocity. So if I have velocity area vector, if I calculate the magnitude and integrate it along xy plane, because there are two independent components, x and y. If I integrate it along xy plane, I get the net area. That is the concept. This is the only way I can calculate the area or area or velocity area vector. Velocity area vector is nothing but dp by dx cross dp by dy. dp by dx cross dp by dy. dA, dx, dy. Full term is called area vector. We use area vector in calculation of flux, if you remember it very well. So area vector in flux, while calculating area vector in flux, is nothing but dp by dx cross dp by dy, where p is xi plus yj plus fxyk. dp by dx cross dp by dy. Now integrating it along xy plane dx dy, full term is area vector. Okay, but we want area, not the area vector. Then whatever is dp by dx cross dp by dy, get the magnitude of it and integrate along dx dy. So this is the fundamental of doing. What is the problem here? Problem is that dp by dx cross dp by dy, if I get the magnitude of it, it comes to such a difficult algebraic equation, it is impossible to calculate the integration. Like x minus y to the power e to the power x minus y whole square. This is the integrand, x minus y to the power e to the power x minus 2 whole square. Now integrate it with dx dy. Now integrate. Now I have to take another help called uv plane. Now u equal to x minus 1, v equal to x plus 1, and then we will do something and we'll change it. So it will be u to the power e to the power u square, something like that. It is far easy now. Okay, but what about dx dy, or x minus y into e to the power x minus y whole square, whatever. If I say x minus y equal to u, then u into e to the power u square is far easy to integrate. U into e to the power u square is far easy to integrate. Okay, if that is the case, then what is dx dy? How to change dx dy into uv? dx dy is nothing but integration over xy plane. So d of xy plane by d of uv plane into d of uv plane. What is d of xy divided by d of uv? This is called Jacobian. Or, 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 I started with position vector p equal to xi plus yj plus zk. Let's do the parameterization here only. So now it is xi plus yj plus fxyk, where x equal to guv function g over uv, y equal to huv, and then function over x comma y, function over guv comma huv. Now if this is the position vector, then what about dp by duv? dp, actually p position vector is nothing but function of x comma y, px comma y, dpxy by duv. Now I am differentiating with uv plane. So when we are saying dp by dx cross dp by dy, actually we are trying to differentiate it along xy plane. That's why it is giving me area. dp by dx cross dp by dy is giving me the, we are trying to, if I have a position vector xi plus yj plus zk, fxyk, if I say dp by dx plane, if I say dp by dx, we are trying to calculate the gradient along x-axis. dp by dy, we are trying to calculate gradient along y-axis. If I say dp by dx cross product, dp by dy, it is equivalent to dp by dxy plane. So we are trying to calculate the variation that is seen in p vector with the any variation that we can see along the any small area region in xy plane. Xy plane, if I take a small area region, if there is a slight change in xy plane, then how much the position vector would change? If xy plane, if I consider as a small rectangular region, then if there is a delta x change along x-axis, delta y change along y-axis, then there is a change of delta x, delta y, whatever it is. If this is dxy, if there is a small change in area in xy plane, how much change it brings in the position vector dp by dxy plane. That is nothing but dp by dx cross dp by dy. Similarly, if I go with parameterization and p was px comma y, position vector with respect to x comma y. Now change it to puv, that is now guvi plus huvj plus f guv comma huvk. Now this is full place uv vector. Then what is the change in p? What is the change in p that is seen with the, if I make a small change in uv plane? dpuv by duv, dpuv by duv, that is nothing but equal to d guv by duvi plus dhuv by duvj plus df of guv comma huv by duvk. This is the change in position vector with parameterization if I make a small change in uv plane. How to calculate it? So how to calculate dpuv by duv? If I leave the uv, if I replace it back with xy, then dpxy by duv equal to dx by duv plane I plus dy by duv plane j plus d of fxy by duv k. How to do it? So that is the question. We will proceed on it. We are not running away. So we will proceed on it, that how we can calculate the end fundamental here is, the end fundamental here is that we have to calculate d of xy by d of uv, because if I go with full place Cartesian, then calculating the area of a surface is nothing but whatever the integrand is, that is dp by dx cross dp by dy, get the magnitude that will come as algebraic equation of x and y, which is very complex dx dy. So dx dy is dxy plane. Now if I change it to uv, integrand easily I can change into uv. But dxy plane changing it to uv plane is something very sweaty. Dxy by duv into duv. What is dxy by duv? If there is a unit change of area in uv plane, how much unit of change of area it brings in xy plane? That is the question. If I have uv plane, I have xy plane, and there is a rectangular region in uv plane. If there is a small change happens in this rectangle duv, if I map this rectangle into xy plane, which may not be a rectangle, some area, how much area change it brings? If there is a unit change in the area dxy by duv, if there is a unit change in the area of this rectangular plane of uv, then how much area change it brings in the xy plane that has mapped from uv, duv, dxy by duv, that is Jacobian, dxy by duv. So if I find that, then I can convert dx dy into du dv and some change, okay, that will come. Dx dy, now it has changed into dxy by duv and duv. duv I can say du dv because it is pure into uv plane. Du dv, but whatever this we are getting dxy by duv, that is the extra stuff that we will get. So dx dy, extra stuff in polar coordinate system is r. Dx dy equal to d theta dr, extra component is r d theta dr. But for any mapping, what is the extra component I get? I believe it's clear. If it is an area, if it is the area that dxy plane, if I take, then that is dx dy. If I take uv vector, duv is du dv. If I map these two so that x equal to guv, y equal to huv, then if there is a unit change in duv plane, I draw one rectangle and there is a unit change on this rectangle. This rectangle maps to some other shape in xy plane as per GU and HUV. If there is a unit change along the rectangle in UV plane, how much unit change of the area it brings in xy plane? It's clear. If this is UV plane, this is XY plane, there is a rectangle I draw in UV plane, centered at the origin. If I map this rectangle in XY plane with X equal to GUV, Y equal to HUV, it may not be a rectangle, it would be some shape which has an area. If there is a unit change area in this rectangle in UV plane, how much unit of change in area I can see in the XY plane? D XY plane by D UV plane. Okay, so the net integration, the net surface area, we remember that was dp by dx cross dp by dy, magnitude dxy plane. Now, if this integrand I change it to uv plane, then this dxy plane integration will change into duv plane. How to change it? That is dxy plane by duv plane into duv plane. duv plane is du dv. DUD. If xy plane is Cartesian, UV plane is also Cartesian. If that, then DUV plane is DUV plane is DUDV. But what is DXY plane by DUV plane? If I make a unit change in DUV plane for the area, it is UV plane. It is area, not a line. Then how much unit change in the rectangle mapped to the XY plane it will bring? DXY by DUV, done by I believe to famous mathematician, but it is not difficult. So anyone would have done it. I did it. Then I found it is already done. So that is called Jacobian matrix, Jacobian determinant, whatever it is. So that is d xy plane by d uv plane. draw a rectangle in UV plane, map it to the XY plane and get the shape, new shape. Make a unit change of the in rectangle of the UV plane. See how much unit change it is bringing in XY plane, dXY plane by DUV plane. Okay, so that we will calculate. So now we are entering into the vectorization, the parameterization of surface in calculus. So that we are not running away. So that we will see.